this section we're going to tackle this node voltage problem that has dependent current sources. And I'm going to tell you right now, this problem is going to take a little while to work, but it's a perfect example of a test problem because it tests your knowledge of node voltage really extensively, and you get thrown the loop of the dependent sources in two different places. It's just a great test problem because it really flexes those muscles. So if you think you've really understood everything up to this point in the course, I encourage you, pause the video right now and just try to work this problem on your paper and then see if you can get the right answer. So we're trying to find what is the power developed by the 20 volt source. What's the power developed by the 20 volt source? And we're going to use the node voltage method to get there. So give it a shot if you want. Go ahead and pause the video, try to work the problem out. There's some work to get to the answer, but everything we've covered up to this point, if you really and truly have understood it, should prepare you for this. The only problem with this, just like anything in math and science, is it's a little more complicated. There'll be probably more equations, a few more steps, definitely more algebra. So we're probably going to fill up all of the boards, all 4 of the boards doing this guy. But nothing fundamentally is more challenging as far as like a crazy twist, all right? So let's get started. First of all, think about what is your end game. What's the power developed by the 20 volt source? Well, here's the 20 volt source. We know that if we're trying to find the power developed by the source, we know the voltage. So to find the power, we need to know the current flowing out of this source. So P is equal to IV, right? We've talked about that. So we need to find this current, right? So we've discussed in the past that once you know the node voltages in a problem, then by definition you can calculate everything else. So what we're going to do is go through and identify the nodes, identify the reference node, solve the problem for the node voltages. Once we have the node voltages, then we'll be able to find the current through there. Once we know the current through there, then we can find the power. So sometimes it's nice to have a big picture roadmap. Let's do the node voltage method, get the node voltages, then find the current through there, then find the power. Okay, that's what my plan is going to be. So let's go and just try to apply everything as we've discussed. So first of all, we see a giant node at the bottom of the drawing, right? This enormous node at the bottom that connects everything. So this is going to be our reference node. And since I have a bunch of text here, I'm just going to put the reference node down here by this little symbol down here. That means this is the common node with which all of our node voltages will be referenced. Now, where are the other essential nodes? Well, here's obviously one giant one on the bottom, but we have one here, 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 and here. So there's 4 at the top plus the 5th one, the giant one at the bottom. So there's 5 essential nodes, right? So under normal circumstances, we would say, okay, there's 5 essential nodes total. That means 4 node voltage equations, which is going to lead to a lot of algebra to solve 4 simultaneous equations. However, we have a dependent source. This is why this problem's a little tricky. It's not connected as it was the last time directly between 2 nodes that are close to one another, but it is connected across the circuit to another node far away. So it does meet the definition. I told you, anytime you have a source, dependent source or not, anytime you have a source connected directly between 2 essential nodes with nothing else, it's going to basically reduce the number of equations that you have. And you'll have to write those constraint equations that we talked about. This definitely fits the bill, all right? So let's first get started by marking our essential nodes. So let me put a giant dot here, and I'll just mark this with a big 1. That's essential node 1. Let me mark this one with essential node 2. I'll put little circles around them so you can tell that those are just labelings for the essential node. This guy I'm going to call essential node 3. Big surprise, this guy will be essential node 4. And so since I'm trying to use a node voltage method, I need to label this. This is node voltage V1. This guy is node voltage V2. This guy is node voltage V3. And this guy is node voltage V4. So far, everything's been exactly the way we've had in the past. You know, this is getting cluttered, so I tried to use some color. The green is already given to you in the problem. You have a dependent source here, 35 times I sub phi. That's a current. I sub phi is defined by the current in this leg. So whatever the current is here, multiplied by 35, that's going to be the voltage across. It's a dependent voltage source. All right. The current flowing through this current source is 3.125 times V delta. V delta is defined to be the voltage across the 1 ohm resistor. So 2 dependent sources, 1 independent source. All right, so the first thing we notice right away, right, is V2 isn't even really in the running for a real unknown, because even though I've labeled it here, we know that V2 is just 20 volts. So here, I guess you could say here's your first node voltage equation. It's not really an equation, it's given to you. It's not explicitly given like V2 is equal to this, but you just label everything and you say, okay, this node voltage is known. So taking stock of where we are, we expected 1, 2, 3, 4 node voltage equations, but one of them is sort of trivial. So really, because of the 20 volt source, really we only expect 3 real node voltage equations, right? But we also notice that we have this source connected directly between 2 essential nodes that we care about. So really, instead of 3 real node voltage equations, we really expect to really only have 2. So you don't really need to keep track of all that. I'm just kind of trying to give you this intuition so that you can look and make sense of what you're trying to do and just do a sanity check. We really should expect to have 2 real node voltage equations and then probably some constraint equations to satisfy and round out the system so we can solve it. So let's just go left to right and start working with node number 1. So the first thing we're going to do is figure out, okay, the current through this leg, there's a current through this leg, there's a current through this leg. So what's the current through the 20 ohm resistor? So let's look at node 1. The current through the 20 ohm resistor is V1 over 20. Very simple, V1 over 20. All right, and then let's find the current through the 2 ohm resistor. So that's going to be V1 minus this voltage, but it's V2, but we know it's 20. So what we're going to have is V1 minus 20. This gives us the voltage across this 2 ohm resistor going this way. Divide by 2, V over R. So far we're doing great. Current through here, current through here. Now let's find the current through here. We immediately run into the same problem we always run into. When you have a dependent source connected directly between 2 things, see, if it wasn't connected directly between 2 things, we wouldn't have this problem. Because it's physically connected directly between 2 things, we can't find the current in that leg. So we have a choice here at this point. Your first bet would be to go ahead and invent this current, this made-up current, whatever it is, I'll call it I, and then just round out my equation with I. And then I would continue writing node voltage equations. When I get to this side, I would use the same I over here, and then this equation for this node and this equation for this node would kind of be related because it has this I in the middle there that we sort of made up. We'd add those 2 equations together, it would eliminate I. That's totally cool. That's totally fine to do that. But I thought this would be a great example to flex your muscles and show you how a supernode can be used, because you get the same result either way. Notice that even though it looks a little bit weird, and I know this drawing is going to get cluttered, you're going to have to forgive me a little bit. Even though this is going to be a little bit weird, this can be considered, believe it or not, a supernode. And this is sort of why I want to show you this particular problem, because of this fact. So let me just finish circling everything here. I know it looks a little bit crazy. Even though this guy is far apart on opposite sides of the circuit, it doesn't matter. You can look at any two things in a circuit that are connected together, basically, and draw a dotted line around the whole thing, and the current flowing into that blobby region has got to be equal to the current coming out of it. It's just physics. It's like, blowing into, a straw. Whatever goes in has to come out. It doesn't matter if I fork the straw a million different ways. If I draw a dotted line around any portion of that straw, where no matter how many times it forks, if I cut through whatever I cut through, the air going in has got to be equal to the air coming out if I make a closed path, right? Same thing here. I'm closing a path between these guys. The current flowing through these legs into this blobby region here and going all through this stuff has got to basically be equal to the current coming out the other side, however you want to think about it, but that's basically the fact. So right out of the gate, we have kind of a complicated equation. We have current going through here, current going through here. Okay, now this is a supernode now. We're going to pretend that this is physically the same node as over here. So the other part of this node is this leg, and this leg. Well, let's work with the currents over there. The current through this 4 ohm resistor is popping up to V4 minus V3 over 4. Okay? Then the current through this leg is V4 over 80. V4 over 80. And then the current through this leg is just a current source. So it's coming out, so we call it positive 3.125 V delta. That's the current. And all this stuff has got to basically be equal to 0. This is a node voltage equation. It is a shortcut because the only other way to get it is just to pretend there's current flowing. Well, there is current flowing through there, but to make up a new variable. And then I would have this stuff plus I over here. When I got to this side over here, I'd have this, and I'd have minus I coming in. And then I'd add those two equations together and I would get an answer. Instead of doing that, I just pretend it's one giant node, eliminate the intermediate step, and say this is a current, this is a current. Okay, this is all connected as a supernode. Then I have this guy, and this guy. The reason it's useful is simply because we don't have any other way to find a current there. So this is a good example of when you would use a supernode to save some time on a test. So that is a node voltage equation. All right, so let's go through. So we've kind of conquered this node. This node is physically connected as a supernode to this one. So we don't have any more equations to write with this node. We're done. They're connected together now, so to speak. This node here isn't even really a node that we care about because I labeled it V2, but we know it's 20 volts, so there's no reason, I even wrote it here, there's no reason to write an equation here because we know the node voltage there. The only other node here is this one, node 3. So let's go and write that. So at node 3. At node 3 over here. So let's find the current through the 1 ohm resistor. We're going to pop up to V3 minus this voltage here, which we know to be 20 volts, over 1, because it's 1 ohm. So we're taking the voltage drop we're finding across here, divided by a 1 ohm resistor. Then we have the current down through here, so we'll have V3 over 40. All right. And then we have the current through here, V3 minus V4 over 4 ohms. And all of this has got to be equal to 0. So make sure you understand this equation as well. Working with this node, this minus this over 1, got that. This over 40, got that. This minus this over 4. Now these are the only node voltage equations you can write in this problem, right? And notice that it makes sense. We said, I just told you a minute ago, that you really should expect 2 node voltage equations. Normally you'd expect 4 of them, but one of them is really trivial, so you don't count it. It's not a real equation, so that would leave 3. And because this connects 2 essential nodes, I told you every time that happens, you subtract 1 equation off. So you should expect 2 node voltage equations, which is exactly what we got. So now we roll up our sleeves and we get ready to solve this problem. We think we're almost done. Of course, you'll find out in a minute we're nowhere near done because there's so much algebra to do. But you look at this and you say, okay, I've got V1, I've got V3 and V4, and I've got V delta. Here I've got V3 and V4. So total number of variables I have is 4. Total number of equations I have is 2. So I'm in big trouble because I can't solve anything. So don't even attempt to substitute anything until you can figure out what the rest of your equations are. Somehow I need 2 more equations to make this system work. And I know right away I definitely need to write an equation involving V delta because that's one of the dependent sources we have on the board, and I suspect later on I'm probably going to write an equation involving I phi also because it's another dependent source. So that's sort of the hint I'll give you. When you're writing these constraint equations, go to the variables of your dependent sources. Those are the constraint equations you need to figure out, how to write. So let me kind of draw a little divider line, and let me write down that the following are the constraint equations. The constraint equations. All right, so let's work with V delta. Let's work with V delta. What can we do? All right, so let's see what we can do here. Let's change colors to green. V delta. What equation can we write with V delta? Well, this doesn't help us over here because it's current. We don't know any of these currents, so we can't do anything with this. But V delta is defined to be what is across the 1 ohm resistor. So when I say, don't forget, when I say write your constraint equations, I don't mean you need to solve for those variables and know what they are. I just mean you have to write some equation, some valid equation, some independent equation that involves that variable and relates it to other node voltage variables in the circuit. You need to have some more equations that make sense with the variables that you have. So it doesn't mean we need to solve for V delta and know what it is. It just means we have to write an equation that involves it. So notice we have a 20 volt source here, we have V delta here, and we have V3 here. So this is easy to write a constraint equation because We know, so I'll write it down here, V delta is equal to, notice what we do all the time in node voltage. We're trying to find, what is the voltage across this resistor? It's 20 minus this guy over here, V3. So it's going to be 20 minus V3. Okay, there's a constraint equation. This voltage as defined has got to be equal to this one minus this one. We do that every time we write a node leg. It would be this minus this over 1. Well, V delta is defined to be the voltage through here, so it's got to be this minus this. There's a constraint equation. So let's go back and look. We have four variables. We have V1, V3, V4, and V delta. So we have four variables. We only have 3 equations, so we need one more equation. So let's go back and look and see and look at this. And I'll tell you right now, you can stare at this for a while before you see what to do, because it is a little bit complicated, and I don't want to say complicated, but it's not easy to see at first. I mean, even when I solve this problem, I'm looking at it and I'm like, geez, where's my other constraint going to be? I've already done something with V delta, so I know I'm not going to do anything else with V delta. I have this I phi here that hasn't been used anywhere else, so I really don't want to write a constraint equation involving I phi. The reason I don't is because I don't have any I phi anywhere else here, so I really don't want to do that. But I quickly start looking, and you know, there's more than one way to solve a problem, but at least for me, I can't figure out an easy way to not involve I phi. So I'm going to go ahead and have to do it. So let's go ahead and figure this out. Let's go and write, I'll switch colors here. What you'll notice is that this source is 35 times I5, and it directly connects this node and this node. So let me show you something cool. The voltage across this entire thing, which is the voltage source, but it's across this node to this node, is going to be equal to, pop up to the voltage here, V1 minus this voltage over here, V4. Would you not agree that the voltage between these 2 points would be the node voltage that I measure here minus the node voltage way over here? It's the same thing we do internally here. You know, you go up to V3 minus V4, that gives you the voltage drop across this resistor. You know, over here it's V2 minus V1, that gives us the voltage drop. When you subtract 2 voltages, it's just telling you what the voltage difference is between those 2 points in the circuit. So what I'm telling you is if I take V1 and I subtract the voltage way over here, V4, and those are these points here, then what I'm left with is the voltage across this entire, you know, thing, which is over here. So I can say that V1 minus, because that's over here, minus V4 has got to be equal to, that's the voltage across here, but what is that equal to? It's equal to this voltage source, which I have up here is 35 times I phi. So that's a constraint equation. It basically tells you how this dependent source behaves in relation to the other node voltages. The only problem is when I write it down, I introduce a new variable that I didn't have anywhere before, I phi. But then you look back at the problem and realize I phi is defined right here. I phi is V3 over 40. So what you write is I phi is V3 over 40. That is what I phi is equal to. So now I look, I didn't really quite get there exactly the way I initially thought I would, but now I'm okay, because what are my variables? So let me go ahead and just kind of do a little aside here. Variables. It's good to write this. We have V1, V3, V4, V1, V3, V4, V delta. We have everything else here, and then we have I phi. How many equations do we have? 1, 2, 3, 4, 5. We have 5 equations, 5 unknowns. That's really not what I expected when I first started this problem, to actually have 5 equations and 5 unknowns, but sometimes when you write the node voltages equations and you write the constraint equations, sometimes you'll need, well, I can almost guarantee you, okay, I'll just tell you this right now, whenever you have dependent sources like this, you're almost always going to involve constraints related to those things. So we know we're going to need an equation with V delta. We wrote that here. We know we're going to need an equation with I phi. That's what we wrote here. And then we go back hunting through the circuit to figure out how we write another constraint because we introduced a new variable that we really couldn't avoid. So we have 5 equations, and what I'm going to do to make it easier to show you what I'm talking about later is I'm going to erase the little labels I have in the beginning here. And I'm going to label these things. I'm going to label these equations. This equation I'm going to label equation 1. This one I'm going to label equation 2. This one I'm going to label equation 3. Whoops, I did the wrong thing. This is not going to be 3. This is going to be 3 right above it. This is going to be 4, and this is going to be 5. And that way, when I'm doing the rest of the problem, I can say, oh, remember back equation 2, this is what it was. When you get so many equations on the board, it's really helpful to do that. So, what this is going to boil down to is solving this system for all 5 variables. And then once you have everything, you'll have all the node voltages. Then you can find the current through the 20-volt source. Then you can find the power through the 20-volt source is delivering to the circuit. So let's go ahead and work with that. There's lots of different ways you guys can proceed. I mean, we can all do it differently. I'm not going to skip any steps though. So what I want to do is basically plug equation 5 into equation 4. Take I phi, stick it in here. That's going to give me an equation with V1, V3, and V4. And then I'm going to try to backward substitute as many times as I need to be able to get a nice set of equations that I can solve with a matrix. So let's plug equation 5 into equation 4. This is why I labeled them, so that's easy for you to reference here in a minute. So what I have is V1 minus V4. So I'm going to have, actually let me switch colors to make it easy to see. I have V1 minus V4 is equal to 35 I phi. So it's going to be 35 times this, 35 V3 over 40. 35 V3 over 40. All right? And so what I'm going to have is, I'm going to tell you right now, this 35 over 40, to keep everything, usually when I do these problems, I like to try to keep the fractions everywhere, multiply by the denominator, and just kind of keep nice numbers everywhere if you can. But I'm going to tell you right now, keeping 35 over 40 around and trying to multiply and keep everything nice and neat is just going to be a pain, especially with so many equations. So here I'm going to break down and start using decimals. And that's just what I'm going to choose to do. You can do it however you like, but that's what I'm going to do. So when I'm doing this guy right here, I'm going to basically say, let me just write it. Yeah, let me write it right here. I'm going to say V1 is going to equal to this guy. 35 divided by 40 is 0.875 times V3 plus V4. All I did was I took the V4, I moved it over to the other side, that's why it's over here, and then this 35 over 40 got changed into a decimal. And I'm going to call this equation, even though it's not really an independent equation, it's a simplification, so I'm going to call it equation 6, just so I can reference that later. Okay, so what I have here is I've effectively eliminated this from the system, right? So I have 1, 2, 3, and then I have the 4th equation, which I just simplified over here. So really I have 4 equations. And notice I eliminated I phi. So I phi is no longer in the equation. So I have 4 equations and 4 unknowns. The 4 equations are this one, this one, this one, and this one. After I've plugged in this, I only have 4 equations and 4 unknowns. And that's what I need to solve for. So next, I'm going to plug in equation 6 into equation 1 and equation 3 into equation 1. And this is all algebra, so you may have your own way of doing things, but this simplified version that I just came up with for V1, I'm going to stick it in here. And then I'm going to stick equation 3 in here. So what's going to happen is, whenever I do that, see, this guy is V1 in terms of V3 and 4. So when I stick it in here, there's not going to be any V1s anywhere. It's going to be V3 and V4, and then V delta. So that's why I'm going to take this one, V delta, and put it in there, which is also in terms of V3. So whenever I stick this in here, and the other guy in there, I'm only going to have V3 and V4 in the top equation. V3 and V4. My second equation only has V3 and V4 in it. So then I'm going to have 2 equations and 2 unknowns. I mean, you could just start here and write a giant matrix expression and solve the system with an inverse. I mean, you could do that, but I'm just going to substitute to make it a little bit easier there. So once I take equation 6, which is this one here that I found, and stick it in there, then I'm going to get the following. So I have V1 over 20. V1 I just found to be this mess over here. So it's going to be 0.875 V3 plus V4 all over 20, because it was V1 over 20. Here I have V1 minus 20 over 2. So V1 minus 20 over 2. V1 is given by this, 0.875 V3 plus V4 minus 20 over, it was over 2. Okay, so I've substituted for V1. This is involving V3 and 4. There's nothing to substitute there, so I'll just copy that over. V4 minus V3 over 4. And then I have another term, V4 over 80. So nothing gets substituted in there. And then finally I have the last term, 3.125 V delta. And I'm going to substitute for V delta here. V delta is this. So I'm going to have 3.125 times 20 minus V3. And I ran out of space, so what I'm going to have over here is plus 3.125. V delta was given over there by 20 minus V3. And all this stuff is equal to 0. So basically I've taken this top equation, I've substituted for V1, I've substituted for V delta. So this looks ugly, very ugly. So that's why I'm going to give up on trying to keep it clean. So I'm just going to have decimals everywhere. So let's just plow through it. 0.875 divided by 20 is going to give you 0.0438 V3. 1 over 20 for this next term, 0.05 V4. I'm just dividing stuff and keeping my variables along for the ride. Now I'm over on this term. Here, 0.875 divided by 2, 0.4375 V3. And then I have a 1 here, so 1/2 is 0.5 V4. And then I have 20 over 2, negative. It's going to give me negative 10. I ran out of space, so let me continue over here. I have 1/4 and 1/4, so I'm going to have 0.25 V4 minus 0.25 V3. Okay, and then over here, 1 over 80. 1 over 80 is 0.0125 V4. Okay, and then I have this stuff here, and again, I ran out of room, so I'm going to just do plus 3.125 times 20. 3.125 times 20 is 62.5, and then I have a minus sign, 3.125 V3 equals 0. Now I can promise you this looks really ugly, but it's going to get really simplified quickly, because what we have, let me switch gears to, why not red? Let's go ahead and collect terms. So here we have a V3 here, we have a V3 here, we have a V3 here, and we have a V3 here. So when we add all 4 of these, you know, this 0.0438 plus this, minus this, minus this, what you're going to get is negative 2.8937 V3. That's what you're going to get. And then for the next guy, let's switch gears so it's a little bit easier. You have a V4 term here, V4 term, V4 term, V4 term. So when you put those guys together, and you add this plus this plus this plus this, what you'll get is 0.8125 V4. So we look at what's left and we see we have a negative 10, we have a 62.5, so whenever we add those together, what we'll have is plus 52.5, and that's equal to 0. So it looked really, really complicated, but in the end, we get an equation in V3 and V4. Bam, we're done with that, okay? And then we look back, so all we were doing was working with the top equation. We plugged in the constraints that we had. We basically beat this equation into a form with V3 and V4 only. This equation is already written in terms of V3 and V4 only. So we're going to write this guy directly below it and basically go to town. So let's simplify this guy right here. Let me switch colors. This guy's just divided by 1, so it'll be V3 minus 20. So V3 minus 20. We have V3 over 40, so when you 1 over 40, I'm just doing the decimals now, 0.025 V3. And then this is 1/4 and negative 1/4, so that's 0.25, so we'll have 0.25 V3 minus 0.25 V4. And this is equal to 0. So let's simplify this as follows. The V3 terms are this term, and this term. So when you take this, plus this, plus this, those 3 terms there, you will get 1.275 V3 The only V4 term we have is negative 0.25, 0.25 V4. And do we have any constants? Yes, we have a 20 over here. We'll move it to the other side, 20. All right, so finally, after all of this, I'm going to kind of circle this equation, and I'm going to circle this equation. Ultimately, that's all we have to solve now. We have an equation in V3 and V4, and actually, I've noticed what I'm going to do here. Instead of setting it equal to 0, I'm going to set it equal to negative 52.5. Negative 52.5. It's the same thing. I just moved the 52.5 to the other side. So I have an equation in V3 and V4, an equation in V3 and V4. I know what's on the other side of the equal sign. I can solve this finally for V3 and V4. And then that's basically going to give me all the node voltages I need, because once we have V3 and V4, I'll be able to go up here, V3 and V4, I'll be able to calculate V1. So at that point, I'll know V1, I'll know V3, I'll know V4. I already know what V2 is. It's just a voltage I already know. So I'll have all the node voltages. So solving the system is the key to the whole problem. All right, so what we're going to do is our trusty matrix method. AX is equal to B. So the coefficient matrix is just everything here. So negative 2.8937. Over here we have 0.8125. Underneath we have 1.275. Here we have negative 0.25. That closes our coefficient matrix off. We're solving for V3 and V4. And on the other side, we have, on the right-hand side of the equal sign, negative 52.5 and positive 20. Negative 52.5, positive 20. This is the matrix system we need to solve for. And by the way, we know when we're going to take the inverse, multiply it by both sides. So in the end, it's going to be equal to the inverse of matrix A times matrix B. So what we're going to be left with is V3 and V4 are going to be equal to the inverse of this matrix. If you put this in the calculator, exactly as written, negative 2.8937, that, this, and this, hit the inverse guy. What you're going to get is a nice inverse, actually, 0.8, 4.08, 2.6, 9.26. That's the inverse of matrix A over here. You still have to multiply it by the right-hand side, negative 52.5 and positive 20. So at the end of the day, V3, V4, take this matrix, multiply, so you cross down, and what you're going to end up with is something kind of shocking. You get a nice 10 up here and a nice negative 29. So it doesn't always work out like that, but it sure does give you a good feeling that V3 and V4 are nice numbers, right? So let me just summarize over here. V3 is equal to 10. V4 is equal to negative 29. So how do we find the rest of the node voltages? All right, so we go back up to some of our constraint equations. We know we have an equation for V1 in terms of V3 and 4. So we can find this. So V1 is equal to 0.875 V3 plus V4. So V1 is equal to 0.875. V3 is 10 plus V4, so it's minus 29. So V1, when you take this multiply by 10 and then you subtract 29 off of there, what you're going to get is negative 20.25 volts. So, just to summarize, node voltage 1, negative 20.25. Node voltage V sub 2 is this node here, but we already know it's just 20 volts. We didn't really even have to solve for that. So let's just write it down for completeness. 20 volts. Node voltage V3 is 10 volts. Node voltage V4 is negative 29 volts. So these are all of the node voltages, and you know from experience that once you know the node voltages, everything else can be solved for. So what you really want to do at this point is use the node voltages that we have, and I promise we're almost done with this problem, to use the node voltages that we have to calculate the current flowing through this leg, the current flowing out of the source, really. And then once we know the current, we can calculate the power. So how do we do that? You really need to think a little bit. You can't really directly calculate the current flowing through this leg by just a quick division or something like that. What you need to realize, though, is that because you know the node voltage is everywhere, I can easily find the current here, and I can easily find the current through here, because I know the voltage is everywhere. So if I can find the current through this 20 or 30 more of them, right? And get really, really comfortable with node voltage. I've tried to really instill the sign convention in you. I've tried to really teach you what to look out for. What do you do when the sources are flipped upside down? What do you do when you have this connected like this? And the kind of the gotchas. And hopefully by now you have some sort of warm fuzzy feeling of roughly how to do this stuff. But if you have just simply watched this video passively as, oh, I think I get it now, don't go take your exam. Go back and work all of the problems that I've worked here by yourself and make sure that you can get them exactly right. And then, once you get that confidence, go work some more. Now we're going to close the node voltage section off, and we're going to go talk and work with the mesh current sections coming up following, which is just another solution method in your bag of tricks to solve circuits. Sometimes node voltage will be easier to apply, sometimes mesh current will be easier to apply, so it's important to know both. The other thing I'll tell you as a roadmap is, don't flush this knowledge of how to do node voltage method after these sections. Because later on when we get to alternating current and we introduce capacitors and inductors and more complicated circuit elements, you're going to use the node voltage method again. It's just going to involve different types of elements like capacitors and alternating currents, but the same basic method's going to be there. So definitely make sure you're comfortable with this. Work more problems, follow me onto the mesh current sections, and work with me there and learn how to do that method of circuit analysis as well. Hello and welcome